In this episode, we will finally deal with practical implementation of various systems. Everything we'll show you today might be easily created with the TME Education Electronics Experiments Kit. For the training to be as consistent as possible, we will deal with each system in a certain order. Firstly, you need to know what you want to create, what elements you need to create it, and how to connect all the parts. The next step is to create diagrams which we will analyze. Then we will present some layouts of elements and connections on the breadboard. Last but not least, we will show you some films presenting operation of created circuits. But before we move to these things, let's discuss a really important integrated circuit. In electronics, there are many various elements, but some of them are especially popular due to their versatility. One of them is NE555 timer. It consists of comparators, a flip-flop, a discharge transistor, and a negator on the output. We will show you 3 applications of this integrated circuit, but first let's move to its principle of operation. The structure has 3 resistors with the same value. They form a voltage divider so that the comparators are supplied with voltage for comparison with inputs. For trigger, it's 1/3 of VCC voltage, and for threshold, it's 2/3 of VCC voltage. At the moment of exceeding the voltage of 1/3 VCC, pin number 2 is set to high. This causes the low state to appear on its output because there is negation. The discharging transistor does not turn on, and this state is negated in order to obtain a high state, which is close to voltage of VCC, on the output marked as number 3. If we exceed 2/3 of VCC on pin number 6, the comparator issues a high state for the reset input, causing a high state on this exit. The transistor turns on and the output will have a voltage close to 0. When we give the reset input to low state, the system will automatically turn on transistor and display 0 on pin number 3. We will soon find out that NE555 can do a lot, and we will be happy to use it. One of the simplest electronic systems that we can create is the S-table multivibrator system. It is a circuit that, in the most general application, switches LEDs between them at a specified speed or frequency, but of course it can be used to switch another type of load. To switch some load, for instance in the form of LEDs or motors, we need transistors. In order to be able to decide on the speed of these changes, we need elements that can somehow change the value of voltage or current in a given time. Capacitors are such elements. If we charge them with a small current, they will charge more slowly than if you would load them with a high current. In addition, the larger the capacity, the more time the charging will consume. We will need resistors for limiting the current and cooperation with capacitors. Now it is necessary to get to know the RC circuit consisting of 1 resistor and 1 capacitor. The main parameter in this circuit is time constant. It is time after which capacitor would be fully charged if the charging process proceeded linearly. It is a product of resistance and capacity in the circuit. After about 5 time constant, you can assume that the capacitor is fully charged. Since the charging capacitor increases voltage on its cladding, you can predict that it will be connected to the bases of transistors. In addition, you can assume that your load will be included in transistor connector circuits. This is our ideological pattern. To analyze this system, it should be noted that there are no ideal elements and situations. What we mean here is that the transistors are not 100% identical, just as the resistors and capacitors have a certain parameter spread. Thanks to this, one side of the system will turn on faster than the other. The way the system works may be very complex for beginners. Let us just say about it that one capacitor charges when the other one is discharging. This discharging turns on the transistor, causing almost immediate switching of the second transistor, discharging the first capacitor and charging the other, and so cyclically. We can see here an example of the arrangement of elements thanks to which we can make this system in practice. This is how the system works with a 9 volts power supply. If you change resistors R2 and R3 to those with a larger value, the system will slow down. Let us consider what will happen when the elements are asymmetrically chosen. In this case, one of the LEDs will shine longer than the other. The previous layout was difficult to analyze, and we had to meet a lot of requirements regarding the value of elements so that it could work properly. Let us try the same task with the help of the already known integrated circuit NE555. This is a schematic diagram. We will see one timer on it and literally a few side elements. The work requires R1, R2, C2 and an element whose value will not change C1. It is used to increase resistance to interference and accidental triggering. Resistors R1 and R2 charge the capacitor. When it receives 1/3 of the supply voltage, the high state is output. When the capacitor continuing its charging reaches 2/3 of the supply voltage by the comparator reaction from the threshold input, the low state is displayed. The switched transistor begins to discharge the capacitor through resistor R1. When the voltage drops to 1/3 of the supply voltage, the cycle begins to repeat. We provide patterns that determine the duration of states on the output. We can also see one time course here. It can be seen that the switching moments occur in the moment of reaching 1/3 and 2/3 of the voltage through the capacitor. Here we can see an example of the implementation of the contact board. This is how the system works. A very similar solution can be found in Trafficator in road vehicles. Its implementation is much easier than in the first case. The systems did not have any stable state. However, sometimes you need to generate one pulse of specific duration, not an infinite sequence. Here we will talk about such a system implemented using NE555 timer. The diagram shows a few small differences. The system in the stable state at the trigger input has a high state. This is due to the fact that the inputs have such a high resistance that we can assume that the current does not affect them and R1 does not have a voltage drop. At the output, we have low state and switched off transistor. At the moment of pressing the button, 0 volts is forced on pin number 2. At this moment, the flip-flop switches off the transistor and displays the high state on out. The capacitor is charged until the voltage is equal to necessary one to reset the output, thus to 2/3 of the VCC voltage. The cycle will be repeated only when this event occurs again at the trigger input. We can also see time courses here. It can be seen that the switching moments occur when the capacitor reaches the voltage thresholds. Here is a practical implementation of the circuit on the contact plate. This is how the system works. We see that the system slams the LED diode for a certain period of time. The power supply voltage was set to 9 volts. Sometimes the system generates very short, sometimes multiple impulses, and our task is to do the work once. Then we can tune such a multivibrator to a bit longer time than the duration of this series of pulses, and we can use this information as one event. In previous episodes, we mentioned controlling a motor using transistor which could turn it on and off. However, there is often a need to regulate motor's revolutions smoothly. It can be achieved by turning transistor on and off fast enough to avoid jerking in the motor. Pulse width modulation, or PWM in short, is a pulse signal with constant period and variable filling, which is a percentage of high state related to the entire period. Here are two examples of pulse width modulation signal. We use this signal because transistor does not generate losses when it's off, and its losses are low when it's on. In indirect work, the power generated is the greatest, so we want the transistor to switch as quickly as possible. NE555 in this application is capable of generating pulses with modulated width. The potentiometer and diodes D1 and D2 are new ones for us. Shortly speaking, the system, depending on which direction the current flows, whether the capacitor is charging or discharging, is led by another diode. The potentiometer is used here to somehow distribute its nominal resistance between generator cycles. When the capacitor is charging, the current flows through R1, D1 and the left part of P1. When unloading, flows through the right part of P1, D2 and the discharge transistor contained in NE555. If we add in circuit D2 the additional resistor of a value, for instance R1, in series, we would get about 50% of the fill in the middle position of the potentiometer. The output circuit consists of a resistor limiting the base current, the motor controlling transistor, our motor, and the protection diode. It is used to suppress negative high voltage pins generated by inductive elements. We can also see time courses here. It can be seen that the switching moments occur when the capacitor reaches the voltage thresholds. Here is an example of connecting elements and wires to the contact board. Here you can see how the circuit operates at supply voltage of 3 volts. In the extreme position, you can see that the engine does not stop and does not reach its full power in the other extreme. This is due to the fact that diodes D1 and D2, due to their voltage drop, limit the range of voltages which is present in some of the input circuits, so that the filling cannot vary from 0 to 100%. Until now, we have only controlled the speed of DC motors. Let's think about what you can do in order to control their direction of rotation. With one transistor, it is impossible to realize, because transistors conduct current in one direction only. With two transistors, you can connect one motor terminal between them and the other one to the ground, so that you can control the motor with one transistor in a given direction. However, you need a positive and negative supply voltage to achieve that. In such a situation, you must ensure that both transistors do not turn on at the same time, because you will cause short-circuit current to flow through them. Transistors can be unipolar or bipolar, the same type of conductivity or different. The decision which one to use will determine control system with protection against short circuit. In practice, you rarely create drivers with such a bridge on your own. You would rather use an integrated circuit with power transistors and control logic. Sometimes the integrated structure contains only control logic, and you have to choose the power transistors on your own. However, such circuits are dedicated only to work with high power. The solution is the H-bridge. It is a combination of 4 switching elements so that you can control speed and direction of rotation. You do not require symmetrical voltage supply. This is a diagram of the H-bridge with motor switched on between its terminals. Note that in the previous solution we cannot allow simultaneous turning on of elements S1 and S3 or S2 and S4, or worse, all. How does controlling such a bridge looks like? The keys S1 and S2 connect as output terminals to the supply voltage. The S3 and S4 keys connect the ground leads. When we turn off each of them or leave only one, the current will not flow in the receiver. When we turn on S1 and S2 at once, the current will also not flow because both outputs have the same potentials, so the current will not flow. The situation is the same when we turn on S3 and S4 at the same time. The situation changes when we turn on two keys placed diagonally between each other. When you turn on S1 and S4, the receiver will be connected between higher and lower potential, which will force the current flow. When we turn on S2 and S3, the current will also flow through the receiver. There will also be voltage but directed in the opposite direction. Let us now swap our keys for transistors. Let us take care of one of the most basic drivers, the L293. It contains 4 half bridges capable of transmitting 1 ampere of current per 1 half bridge. The version with the letter D at its end contains the protective diodes in its structure and can transmit up to 600 mA of current. It has control inputs marked with a half bridge number and the letter A. The outputs of the half bridges are analogous outputs with the letters Y. The inputs 12EN and 34EN turn off the half bridges with the numbers shown. The control is quite simple. The state given on input A is repeated at the output Y. If on 2 inputs A we set the opposite states and between the outputs Y turn on the motor, it will start working. When you invert both states at the A inputs at once, the motor will work in the opposite direction. Note that providing 2 high or low states does not create a short circuit risk. Let us consider a situation when you need to use a motor control system with a potentiometer, an on-off button and a button to change the direction of rotation. To generate the course regulating rotation speed, we will use circuit with NE555 timer. It generates PWM signal on its output. We also decided to use buttons with 1 stable state. Simple systems based on D-type flip-flop will help us. The combination of the inverting Q-negated input with the D-data input will create a system that will change the output state Q to the opposite at the moment of voltage rise at the CLK input. Systems with resistors and capacitors on the CLK inputs are used to eliminate the so-called contact vibrations. In practice, pressing the switch generates vibrations, which is revealed by fast switching on several times until the mechanism has stabilized. LEDs marked as D3 and D4, depending on the state at the output Q1, indicate the direction of rotation. Let us analyze the combination system realized using NAND gates. The connection of 2 inputs of one NAND or NOR gateway results in the same operation as the NOT gate, the negating signal. Output Q2 turns on/off both used half bridges of the L293 system, marked as U1. In addition, we note that the diagram has small blocks with 100 nanofarads capacitors. We have already mentioned about the use of these elements. They are used here to filter the supply voltage. Their application is even the more desirable because the motors belong to the elements generating a lot of noise. Here we have included a proposal for such a system on the contact plate. Please note that some contact plates have half-separated power rails and must be connected by wires ourselves. Here is how the motor controller with the H-bridge is working. Now we have fast revolutions. With the potentiometer, you can control the speed of revolutions. The button here lets you change the direction of revolution. The second button lets you turn the motor off. In this part of the course, we will create a system counting number of claps. Firstly, we need to consider which functional blocks should be used. The first one is microphone. The signal it generates is weak and it has a very low amplitude. It must be strengthened so that logic systems can recognize sound as signal close to high and low levels. If we only amplified the signal from microphone, it would turn out that our counting system would charge impulses in too many moments. We are only interested in single counts during claps. Here, monostable multi-vibrator system is useful. Lastly, you need a counting system and an additional circuit presenting the numbers on the display. Let us analyze this layout. Electret microphones are for us like capacitors, where one of the cladding is an acoustic membrane. When it begins to vibrate, stimulated by sound waves, the gap between them changes and thus their capacity changes. In standby, the microphone has full power supply voltage. When it starts to work, the variable capacity will force the current flow through the microphone to R1. This will start switching on the first transistor, which somehow amplifies the signal from the microphone. The second transistor analogically amplifies the signal even more. The capacitor is connected between the output to the amplifier, and input NE555 decouples the fixed component. It allows to pass only to the variable signal. The system on the NE555 already at the first stronger signal latches at the output a pulse with a duration so selected that at one clap there is one impulse and that at faster clapping do not omit any that you want to count. The CD4029 system is an integrated pulse counter. Outputs marked as Q1, Q2, Q3 and Q4 are used to represent the counted number in binary form. The rest of the pins were connected so that the counter counted forward, incrementing the value. It showed us the number in the form of BCD code, counted from 0 to 9. The 4-bit code is then transmitted to the CD4511 decoding system. Its task is to interpret a 4-bit value so that it can be displayed correctly using a 7-segment display. A set of 7 resistors is necessary to limit the current of the LEDs in the display. It has a configuration of diodes with a common cathode. This means that we have 7 anodes and they are all connected by a cathode. It should be connected to the ground. In the case of displays with a common anode, we connect it to the power supply and the pins of individual segments are controlled by an inverted signal. Here we have an example layout on the contact plate, which we suggest you to do yourself. This is how the system works. You could see that system counts claps. However, it should be mentioned that it is really sensitive to any loud sound. If it is music or repetitive impulses, it will count it several times. This is why the counter adds numbers bigger than 1. These were all of our proposals of layouts that you can do yourself on the breadboard. We encourage you to implement your own ideas. In the last class, we will focus on assembly of the system using soldering, and we'll show you a system that is almost indispensable in electronics studio.